What we have seen in the previous classes, we are considered about the sample mean because sample mean should be as close as possible to the population parameter mu. So for that, we'll be writing symbolically. Means how much it is going to deviate, it should deviate less. That is what our concern is. So we'll be writing mathematically for any epsilon greater than 0 and 0 lesser than eta lesser than 1, there exists an integer n such that n should be, the size of the sample should be greater than or equal to, this is population's dispersion. Okay, population's standard deviation sigma square divided by epsilon square into eta. Okay, how you got all this? This is from a mathematically calculated one, right? Okay, this is mathematically calculated. Then your size of the sample should be greater than this quantity. Means population standard deviation square divided by epsilon square by eta, where sigma square is the finite variance of the population. So how you can write mathematically? That is probability, means how much it is going to deviate. That is the distance between x bar and mu should be lesser than epsilon. Okay, and this probability should be greater than or equal to 1 minus eta. Okay, eta is a number very close to 0, right? 1 minus eta will be close to 1. The probability is close to 1. What do you mean by that probability is equal to 1? Means when you say probability of A equal to 1, means what? It is, what to say, the complete, right? Probability of A equal to 0 is an impossible event. Okay, this is sure event. Okay, that is what you mean. So, very closer to 1. Very closer to 1 means it is a sure event. And that is distance between x and mu is very closer to 0. So, probably this can be written in terms of say x minus mu na modulus, that can be written mathematically as minus epsilon lesser than x bar minus mu lesser than epsilon. One minus eta, right? We know that modulus of x is lesser than a, means minus a lesser than x lesser than a. Using this concept only we are doing, right? So this probability, whatever it is, probability should be greater than or equal to 1 minus eta. Eta is very close to 0, means the ultimate answer should be very close to 1. That is what you want to say. That is probability of any event is very close to 1. It's a sure event, right? Sure event in the sense it is this a x minus x bar minus mu lesser than epsilon. This one means the whatever comes in the x bar minus mu, it is very closer to 0. Means x bar is very closer to mu. That is what you mean here. Right, here with this example we have to try to understand the law of large numbers. So that is more observation. If you take the sample size is more, to increase the sample size means we are very closer to the population. Means if you want to find the means mu, if you are increasing the size of the sample, that is if you that x bar whatever you are calculating from that, it will be very closer to mu or population parameter. Means when the size increases, then it will, size of the sample increases means we are going closer to the population. Okay, for this we will see one diagram to make it a bit under, means that diagram will make you a bit clear, right? Suppose the distribution of the weight of all young men living in a city close to the normal distribution with mean. So you are taking a city, right? We are taking a city. Suppose we are taking a city. The distribution of weight of all young men. What you are taking? Weight of all young men. Okay, weight of all young men. Suppose the distribution of the weight of all young men living in a city is close to the normal distribution with mean equal to 65 kg. What is that? Mu, right? 65 kg, and standard deviation equal to 25 kg. Something is given to you. To understand the law of large numbers, means the previous explanation of law of large numbers, we'll try to understand it bit more than that. Means whatever we understood using mathematically, that is probability of minus epsilon lesser than x bar minus mu lesser than epsilon, and this probability is greater than or equal to 1 minus eta. For that we are doing this example, right? So sigma is given as 25 kg. To understand law of large numbers, right, we calculate the sample mean x bar varying from, now you will take the sample from this one sample whose size is n. Okay, means S1, I can call it as S1. Only one you are taking here in this sample, right? The size is n means only one observation. Okay, another sample S2 whose size is 2. Okay, only 2 observation you are taking. Another sample S3 should be inside, it should not come outside. It is 3. Another S4 whose sample size is 4. Something like that you are taking. Means how when I take a sample whose size is 4, whose size is 1, whose size is 2, whose size is 3, when the n number of size, the size of the sample increases, what we are going to ultimately what you are going to see. That is what we are bothered about. When the size of the sample increases, is it closer to the population mean or it is far away from the population mean? That is what our concern is. First we have find the behavior of the sample mean, weight x bar of men chosen at random from the city. So now we will plot the graph. So what we are going to take in the graph is nothing but the plot of the value of x bar. We are going to plot the value of x bar all along the vertical axis. Okay, and the size of the sample on the horizontal axis. Okay, we are going to plot the graph like this. Here I am going to take size of the number of observation or size of the sample. N. Also you can call it as the size of the sample. Here we are going to take mean of, what you are going to take the size of the sample, the plot value x bar. So the mean x bar we can say. Okay, mean x bar. I'm going to take the mean x bar of particular, for example, if the sample size S1, I'm taking the sample S1 now whose size is 1. For that, what is the x bar? That is what I'm plotting, right? Suppose I'm taking it as 5, the size of sample is 5, 15, 30, 45, this is at random I'm taking, okay, 100, 500, 1000, okay, 0. Here I am taking the 61, 63, 65 actually this is what my right population mean. 65 was my population mean, right? That is what we took now. Population mean equal to 65. Okay. Now, as the size of the sample 65, 69, 71. Okay. Somewhere it starts, then it goes down. The curve will be like this, somewhat like this, and it goes up like this, and like this, something. Okay. Imagine it goes up, and goes down, then goes up somewhere, goes down. Slowly, this will something, it will trace like this, and then it comes closer, right? Then it comes very closer to our population mean. That means as the size of the sample increases, can you see? As the size of the sample increases, you are getting X bar becomes closer to the population mean. So X bar is closer to the population mean. This graph clearly states that as the size of the sample increases, we are going very closer to the population mean. So this process will continue. From the graph, we can see that the mean of the sample changes as we make more observations. Eventually, however, the mean of the observation get close and close to the population mean 65 kg as the sample size increases, right? We'll see an example for this. A pathologist wants to estimate the mean time required to complete a certain analysis, right? Wants to estimate the mean time required to complete a certain analysis on the basis of sample study. Okay, so that he may be 99% confident that the mean time may remain with plus or minus 2 days of the mean as per the available records the population variance is 5 days. What must be the size of the sample for this study.